Hi again, Calc BC. Welcome back. And today we're all about polar coordinate systems. So as you know, we use in the beginnings of calculus, we use the Cartesian coordinate system, XY system. And that works really well for a lot of things, obviously. And for the most part, the calculus that we do is done in that Cartesian system. There are, however, multiple coordinate systems, and some of them may work better than others depending on the application. And so today's first look at another system is looking at polar coordinates. I think you've probably seen them before. It was something you might have seen in pre-calculus. So I'll do a quick review of what polar coordinate means. Then we'll take a look at, okay, so if this is how we define polar coordinates, how do we describe those points in polar coordinates when they've been given to us in rectangular coordinates, or vice versa? How do we get from a polar graph coordinates into a rectangular system? Then we'll look at some functions, and we'll wrap it up by looking at some calculus. So let's get started. Give me a quick second to get my share going here. And so polar coordinate system, just like in the Cartesian system, okay, when we're looking at, XY graph like the one here, we have two axes, typically in Cartesian coordinate systems. We have the x-axis and the y-axis. Okay, and if we describe a point like, let's say this point right here, we would say that is 4, 3. The x coordinate comes first, the y coordinate comes second, and everybody's used to that system. Okay, but there's another way we could describe that position in space. The origins location was kind of arbitrary here. It's just where I crossed the two axes. So what if I redefine space so that it's not an XY pair, a Cartesian system like that, but rather it's one based on a distance from the center and an angle. And that's really what polar coordinates does. It says, look, instead of this, let's get rid of the y-axis. Okay, and let's not call this the x-axis. Okay, we're going to call this the polar axis. This is the pole. This is the polar axis. And rather than describe the position 4, 3 as over 4 and up 3, we say, oh, well, actually, that position can be determined by measuring the radius r and going up an angle theta from the polar axis. So while 4, 3 is the Cartesian coordinates, this actually has a different kind of coordinates, and in polar coordinates, we list them as r comma theta. Probably makes sense. Think of it as a point on a unit circle if you want. There's lots of ways to sort of visualize this using the pre-calculus stuff that we've talked about. But basically, every point in space can be defined in terms of the angle you measure from the polar axis and the distance you are from the pole. The polar coordinate system is really handy when you're dealing with things that are not moving along maybe vertical or horizontal lines. Okay, think of this like, if you had an air traffic control center, okay, the tower at SeaTac is the pole. Okay, and then every aircraft that they keep track of, they don't do it on an XY grid. They keep track of where it is in terms of its heading, its bearing from the SeaTac and how far out it is still. So yeah, polar coordinates actually has some pretty good uses, and we use them quite a bit. How could we convert our angle, our point 4, 3 into a radius and an angle? Well, if you're thinking, well, gosh, that actually looks a lot like a right triangle in there, you would be exactly right. And we just use some right triangle trigonometry. You already know that on the unit circle, right, the x coordinate is the cosine of theta. Okay, Um, so, we just use that same basic idea. Look, the radius, of course, in this one is 5. I made it easy on us, right? It's a 3, 4, 5 right triangle. Okay, so we already know r is 5. So we just need to know what theta is. I think, because the radius in this one turned out to be an integer, there's lots of different ways to come up with theta. But typically the one we use the most is tangent of theta, because then that uses, notice the tangent of theta would be the y coordinate divided by the x coordinate, right? It'd be 3/4, opposite over adjacent. And so the tangent of theta in this case is going to be 3/4, which unfortunately is not on the unit circle. 3, 4, 5 right triangle, and it doesn't have an angle that's usually on the unit circle. So theta then is simply the arctan of 3/4. And so the point 4, 3 in polar coordinates can be written as 5, comma, arctangent of 3/4. Now, arctan of 3/4, obviously, we could actually get the decimal for that, but for our purposes right now, leaving it as arctan 3/4 probably works just fine. Later on, you'll see in the book where they've worked out some of the angles because they were on the unit circle or something like that. Let's try with another one. This is an example from your book. It says, take the point -1, 1 and convert that to polar. All right. I'm going to draw a quick graph just because I like to keep it in my head that we're actually talking about -1, 1 here, this point. And so I'm going to mark off my radius here. And you can probably already see that the radius is going to be the square root of 2, right? So let's mark it in here. R is the square root of 2. And so what we need to do then is just figure out how we're going to figure the angle out here. And that's where I'm going to say, look, the tangent of theta is 1/-1. So what angle has a tangent of theta that's equal to -1? Well, this is where you have to be careful with arctan. Okay, because theta, arctan of -1. Remember that the arctan function will only return values from -π/2 to π/2. Okay, its range is restricted in order to keep it a function. Okay, so thinking back to the unit circle, arctan, it only gives us values on this side of the circle. Okay, and so it's going to give us a value down here for arctan, okay, which is -π/4 radians. Okay, but look, that's not the chord. That's not even the quadrant that we want to be in. That's quadrant 4 down there. We want to be, whoops, sorry, bumped the screen there. We want to be over here in quadrant 2, right? Because that's what quadrant our point is in. Okay, and so that's where we have to remember that the inverse trig functions, especially as we get more into converting Cartesian coordinates into polar, the inverse trig functions are restricted in their ranges. They give you the reference angle. You have to know why you want the one in quadrant 2. Well, what's the angle in quadrant 2? Well, if -π/4 is the reference angle, we need to go this way, 3π/4 radians. So our final answer here is √2, 3π/4 for the coordinates for -1, 1. Makes sense? Okay, so you got to watch out. You got to watch out when you're converting these rectangular ones into polar coordinates. Okay, what if we want to go the other direction? What if I give you a polar point, and I want to know, okay, let's go back to our tried and true, right? Everybody likes our good old, Rene Descartes was a smart man. He put that Cartesian coordinate system together on purpose. So how do we convert back? Well, thinking about that right triangle again, Okay, you're going to be given r and theta, but now we need to come up with an x coordinate and a y coordinate. And you're probably already thinking, well, couldn't we do something with some right triangle trigonometry? You sure could. The cosine of theta, for example, right, is adjacent over hypotenuse, right? So solve that for x, and you get x is equal to r cosine theta. Let's go to the sine of theta, right? Sine of theta is equal to y over r, opposite over hypotenuse. Well, that means that y is equal to r sine theta. So there's a nice easy conversion back to get us back into our Cartesian system. So if I said, okay, here's the point. It's the point 2 comma pi. Okay, so let's graph that point in polar. Change to red, why not? Here's the pole. Here's the polar axis. So we're going to go a distance of 2, okay, at an angle. What's that do? Well, that's just a highlighter. At an angle of pi radians. So I'm going to measure pi radians, which actually takes me over here. And then I go out a distance of 2, 1, 1, 2. So this point here is 2 comma pi. All right, let's convert that into a Cartesian point. Okay. Yeah, I'm skipping a line. I should have made the graph paper a little bit bigger, so I'm skipping a line for like a half. Okay. Well, I know my x coordinate. Got a nice little equation for it here. X will be 2 cosine pi. Well, that's nice. Cosine of pi is -1, so x is going to be -2. Oops. Y is going to be 2 sine pi, and of course, sine of pi is 0, so y is going to be 0. And as you could probably tell, if I throw my y-axis on here, you can see that that point's actually -2 comma 0 in the Cartesian coordinate system. So very nice, very easy. Using some trig, we can convert between the two systems pretty smoothly. Individual points, no problem. Okay. Now, let's talk functions. Okay, typically in polar, okay, polar functions, okay, they're given as r equals some function of theta. That's usually how they're given. Okay, so however they provide you that information, they make r some function of theta. However, there's always the tricky ones when there's no theta in it. And I'll show you what I mean here with a couple of examples. But that's typically how we give our functions. So for example, I'm going to give us 3 here. Okay. So let's start with r equals 2. What we're saying is the graph is just dependent upon the radius. There actually is no theta in here. So if I think about the polar graph, oops, what's a polar graph look like where r is equal to 2? Well, it's here and it's here and it's here and here, and it's out here and it's over here and down here and down here. And sure enough, what's it going to look like? Oops. Let me jump over here, and r equal, oh, sorry, I was playing with the slider earlier. R equals 2. Look at that. It's just a circle. So nice and easy. R equals 2 is a circle. Okay. Why it's so hard to switch between apps sometimes. Okay, what is theta equals pi over 3 going to look like? Well, it's all the points. Notice there's no r in this case. It's just theta equals pi over 3. Well, theta equals pi over 3 is a 30-degree angle. So that's what a line looks like that goes through the pole r equals pi over 3. And so that one is pretty straightforward as well. So we have our circle of radius 2. Oops, I didn't draw it very well, but you saw the graph earlier. We have the line, pi over 3. This one, this last one though, now we have r dependent on secant of theta. And this guy, I think what we might want to do with this guy is convert him back into a Cartesian coordinate so that we can kind of visualize it. We'll talk about how we go about graphing some of the more complex ones that aren't as easy to do this with. Because notice that this is r equals 1 over cosine theta. Okay, and so if I move the cosine theta to the other side, I get r cosine theta equals 1. And if you remember, x equals r cosine theta was the conversion. That's why I chose to go that way with this one, because this is just x equals 1. So this is just a vertical line. Here's the pole. Here's the polar axis. Here's 1. And x equals 1, you know, r equals secant theta is just a vertical line like so. Okay, but that one's actually a little bit easier to see if you convert it back into Cartesian. Okay, what do we do when it's not quite that simple? Well, there's some interesting graphs that we see show up time and time again, and they have some features that you can predict. And so we'll talk about how to make a graph first here just by plotting some points. And I think you're going to see that it feels a lot like what we did with parametric equations, which probably helps you understand why we did parametrics beforehand. So here's my equation. R equals 2 cosine 3 theta. And what I'm going to do is I'm going to make a little chart. I'm going to make a little r theta chart, right? Oh, I put them backwards though, didn't I? Because r depends on theta. So there's theta, there's r. And we'll just pick some pretty common values for theta, you know, like 0, like pi over 6. It's getting multiplied by 3. So, you know, maybe we'll do pi over 3. Maybe we'll do a pi over 2. Maybe we'll do 2 pi over 3, whatever. You know, just thinking about as we go around the circle. I'm still, you know, the pi over 4 would be fine too, but let's see what these ones do for us. So if theta is 0, then we get what? Cosine of 0 times 2, we get 2. Okay. If theta is pi over 6, notice when you put pi over 6 in for theta, you get 3 times pi over 6. That's pi over 2. So now we're back to 0. Okay. Then at pi over 3, oh, but oops, we get negative when we plug it in there times 2, we get negative 2. Okay. But then at pi over 2, we get 3 pi over 2, cosine of that 0. 2 pi over 3 times 3 is 2 pi. So it has some pretty strange behavior, right? Let me start mapping this out here. So at 0, when theta is 0, I have a radius of 2. So I'm going to change my color pen to, oh, I don't know, blue again, I guess. Let's go 1, 2. And so here, but then by pi over 6, you can see we come back to the origin or the pole. Now at an angle of pi over 3, okay, we're actually going to go negative 2 units. Now this is what's really weird about polar. So here's pi over 3. Let's say this is pi over 3. Why I'm extending it, you'll know in a second. I'm going to go up that angle. But then if I normally would go along that angle 2 units, I actually go backwards because my radius is -2. Okay. And you can see pi over 2, I'll go back to 0. And then at 2 pi over 3, 2 pi over 3. Okay, so that's, well, here's 1 pi over 3. Here's 2 pi over 3 over here. But notice my radius on that time is 2. So I'll just go out 1, 2 on that. So I've got these 3 points. I'd like to know a little more about what's happening inside. Well, if you were to pick something in the middle like pi, like pi over 9 or 18 or whatever, pi over 12, let's say. Then you'd have pi over 4 cosine, which is √2 over 2. And then times 2, you'd have square root of 2. Pi over 4. Let me move these guys out of the way here. We'd be at √2, which is a little bit more than 1. Oops. There we go. And so you can see we're going to kind of backtrack through in this direction. Okay, so there's an orientation. I probably put this dot a little too far down there, to be honest. The radius is only 2, so. And I am terrible at drawing these when I'm trying to do it slowly and explain. It's kind of one of those things where it's easier if you just kind of let it flow. And we get this kind of interesting looking flower petal thing. I'm going to let Desmos do it. Oh, I was playing around with the equations earlier, but let me change this guy here. It's supposed to be 2. Turn this guy off, turn this guy back on, and there we go. There's what it's supposed to look like. Oh my gosh, that's the wrong one. I'm so sorry. That's a sine one. I was experimenting with Desmos earlier to make sure that it would work, and it does. There it is. So you can see we start out here at 2, and then as we go around the leaves, okay, it makes this little flower petal graph. Notice that there's 3 petals to the graph here, okay, and notice that the length of the petals is 2. That is not a coincidence. Okay, as you saw earlier, I was playing around with the number of leaves. If I make it 5, well, look, there's 5 petals. Okay. If I make it 2, though, there's 4 petals. Okay, and if I make it 4, there's 8 petals. Okay, so you can see what's happening, right? Whenever the coefficient of theta is odd, like here's 7 and there's 7 petals, we get that number of petals. But if you do an even number, yeah, you get twice as many petals. Okay. But there's the graph that we were just working on. And like I said, there is an orientation to this graph, and that's the thing that is important to remember, that when we orient our graph, okay, I want to get, trying to get out of there. There we go. When we orient our graph, okay, there is a direction to it, and it goes this direction. Oops, grab a pen. There we go. It's going this direction. Okay, as theta increases, it follows around this path. Okay. So there we go. That's making a nice polar graph. And this is a cosine rose curve is what it's called. Now, I'm going to jump over the calculus for just right now and say, if you were to go up to page 690 in your textbook, Okay, it gives you some examples of different shapes of graphs that we get when we graph polar equations. Okay, so I'm going to go back over to my Desmos here, and okay, we saw the cosine rose curve. Here's the sine rose curve. Okay, notice it is different. How is it different? It's rotated. Okay, how far? Well, pi over 2, right? So, they are slightly out of phase with each other. Okay, we've known that for ever since we started graphing trig functions. So those are the two for sine and cosine. There's this graph. This is called a cardioid graph, and it's a very interesting graph because you can see that it has this 0 point here, and then it goes around in this big loop. Okay, and then depending on how we change things, we can create an inner loop inside of it. So the big thing here is if I make the ratio of the coefficients in here different, the 1/2 ratio here, I can change it and make a loop inside. I can make it back to 1. Okay, I can make it 0.5, and then it kind of just gets a flat spot on there. So there's different ways to look at that graph as it gets made. Oh, and the minus sign flips it around, so it goes the other way. Okay, and if you change the trig function, you change the whether it goes vertical or side to side. Let me add the sine function there. There we go. So there's the sine wave one. Okay, and again, create the inner loop by multiplying in there. So you see that graph show up quite a bit. The cardioid graph shows up a lot. If I put it back to a ratio of 1, then it goes back to this graph that just looks like a dimpled circle, like somebody took the bottom of the circle and poked it into the center. Okay, and then fiddle around with the coefficient there, you can create these loops. Okay, and again, when we look at the graph, as we start to think about the graph, one of the things that's going to come into play is going to be the orientation of the graph. Which way are we going as we go around the thing? And I think you can see pretty easily that this one kind of goes counterclockwise as well as we go around it. Okay, let's talk calculus. When we did the derivative before in parametrics, okay, we talked about how when we talk about the slope of a tangent line, we still are talking about dy dx. And that's still the case in polar. We still want to talk about rise over run. So how do we reconcile that with the fact that these curves are being defined in totally different ways? Okay, well, you want to think of y and x as being defined parametrically. Okay, they're just being defined in terms of 2 parameters. So that's the key here, guys. X is being defined in terms of r and theta. Okay, y is being defined in terms of r and theta. The thing is, remember that in polar, r is actually some function of theta, right? So another way to think of it then is, and this is the way we're going to have to think of it, is that the x coordinate is the product f of theta times cosine theta. And the y coordinate is r, which is some function of theta times sine of theta. Now, why is it important that we designate them a product? Yeah. When we did this parametrically, right, we said, oh, yeah, that's right. Okay, because the parameter that we're defining these in terms of, right, is theta. R is a function of theta. Okay, so we want dy over d theta and dx over d theta. Dy d theta then needs the product rule. Dx d theta needs the product rule. Yeah, so this does get a little dicey when you get in here, because what we see is, oh, I got you. So in order to find dy d theta, right, we're going to take f of theta cosine theta, right, derivative of sine is cosine, plus f prime of theta sine of theta, and we're going to divide that by, okay. Now, of course, there's a negative when we derive cosine, right? So we get negative f of theta sine theta plus f prime of theta cosine of theta. And that is how we find the slope of a tangent in a polar graph. Okay, so let's think about this for a second. Okay, if the derivative of y with respect to if dy d theta is 0, okay, then what kind of tangent line do we have, right? We have a horizontal tangent. Okay, what if dx d theta is 0? Well, yeah, if dx d theta is 0, then we have the vertical one. Right? We talked about that in the parametrics as well. Oh, I should have said we have. I left the word have out. A vertical. However, if they're simultaneously 0, okay, then we don't know what. But then what does Dr. Lars say? He says, then no conclusion can be drawn. Yeah, no conclusion. All right. Yeah. So if you get both dy d theta and dx d theta equaling 0 at your point, yeah, you don't know what the tangent line is going to look like. So then you're going to go back to the graph and try and figure it out. So, all right. Well, let's try one here that we can take a look at, and then I think that's probably enough with one example. We're going to look at a cardioid. And so let me get my my equation on here. Oops. My Apple Pencil seems very sensitive to the double tap. Yeah. All right. So I have R equals 2 times 1 minus cosine theta. And just real quickly, what's that graph going to look like? Let's check it out. We have R equals 2 times 1 minus cosine. Where's my theta? Here it is, over here on this one. And let's turn the other guy off. Turn off. There we go. And so the idea is, let's figure out where we have horizontal and vertical tangents for this graph. Okay, so we can kind of see them in here right now. We've got some points here. And another point, down here probably somewhere, where we're gonna have some horizontal. You can see we're gonna have some vertical tangency here. That one should be easy. But shouldn't we probably have some vertical tangents back here on the top and bottom of this, where we have the indentation? Probably. Okay, so we want to find all these points of tangency, where I think the problem says, find the horizontal and vertical tangents to the graph. So let's get back to notability and try it out. First things first. those out of there. There we go. Let's just take a look at what dy d theta even looks like. Okay, so dy d theta. Okay, well, let's remember, y is equal to r sine theta. Okay, so we need the derivative, right, of sine. Okay, that's nice. That's cosine. So we get 2 times 1 minus cosine theta times cosine theta. Okay. Plus, okay, well, what's the derivative of 2 times 1 minus cosine theta? Okay. Oh, well, that's just sine. That's it's a -2 cosine derivative, which is 2, which is a 2 sine theta times sine theta. Let's see here. That's 2 sine squared theta. And so we want to solve where this is equal to 0. And if you remember your trig solving, the idea is to try and factor, if at all possible, because then you have the product so that you can set equal to 0 the individual terms using the 0 product property. Well, how can we make this into something that we can then factor? This is cosine theta minus cosine squared theta plus sine squared theta. And almost factorable, right? Well, remember that sine squared theta can be rewritten in terms of cosine squared theta, right? It's 1 minus cosine squared theta. So and now you can see you can move some stuff around. Oops. And 2. So we have cosine plus 1 minus 2 cosine squared thetas. And that's factorable. So 2 times well, let's see. Yeah, take the negative out. That'll change all these signs. That'll be easier. Yeah, so now we got 2 cosine theta plus 1 cosine theta minus 1, 0. And look at that. Now you can solve those separately. Where does cosine of theta, cosine of theta minus 1 equals 0? Well, where does cosine of theta equal 1? 0 and 2 pi. Okay. How about where does 2 cosine theta plus 1 equals 0? In other words, cosine of theta equals -1/2. Well, cosine equals a -1/2 over at 5 pi over 6 and 7 pi over 6. And so those are the spots where we're going to have our horizontal tangents, because that's where dy d theta is equal to 0. If I go back to my graph, and I think I can graph on here, theta equals, what were my, pi over 6, right? Pi over 6. Oh, it doesn't graph those lines. Sorry, you can't graph theta as a function of anything yet. Well, shoot, Desmos, thanks. But if you think about the theta equals pi over 6 line, you can see that we would probably get our horizontal tangent somewhere. Oh, sorry, along that line, theta equals pi over 6. But shoot, I didn't know Desmos couldn't do that, guys. Sorry, I guess they were still a little catching up to do on Desmos for the polar graphing. So anyway, so there's a quick example of finding horizontal tangents. Oh, vertical tangents, we would do the same thing for dx d theta. So just take dx d theta and which is right here in the denominator. Set that equal to 0, and that will be where you'll have your vertical tangent. So, all right. Well, I think that's a pretty good start for you guys on polar graphing. So we'll talk some more about that in class on Monday, or Tuesday. All right. Thanks, guys.